The Blind Inference Handshake. Apple Private Cloud Compute 2.0 ships your prompt data to third-party data centers without ever granting the host or the model provider the encryption keys to read it. This is not a standard cloud encryption layer where the provider holds the master key for maintenance or debugging. Instead, PCC 2.0 utilizes a hardware-level cryptographic attestation that requires a signed manifest of the entire software stack before any data is decrypted. If a single byte of the inference kernel or the operating system is altered on a Google Cloud or NVIDIA node, the hardware refuses the handshake. This mechanism effectively treats third-party infrastructure as a zero-trust execution environment, ensuring that models like Claude and Sol operate in a vacuum. By stripping the provider of privileged runtime access, the protocol moves privacy from a legal agreement into a silicon-enforced constraint. The hardware ledger check? To manage the move beyond Apple Silicon, the 2026 rollout of PCC 2.0 introduces an append-only hardware ledger to prevent supply chain tampering. Every physical component in the third-party fleet, including the NVIDIA Blackwell GPUs and Intel CPUs with trust domain extensions, is tracked independently. Apple does not rely on the cloud provider's own identity verification. Instead, the user's device validates the hardware root of trust through multiple independent vendors before sending a single packet. This stack creates a nested isolation layer where the Titan chip anchors the security, the CPU isolates the memory domains, and the GPU handles the confidential compute. While this multi-vendor attestation adds roughly 40 milliseconds of latency, it creates a verifiable chain of custody for every instruction the model executes. Enforcing stateless amnesia. The primary technical hurdle for private cloud inference is the risk of data residency in memory caches. PCC 2.0 solves this through a forced statelessness policy where the memory controller flushes the entire L3 cache and resident memory between every individual inference call. Standard cloud GPUs often leave residual data in the frame buffer that can be exfiltrated through side-channel attacks, but the PCC 2.0 kernel enforces a hard reset of the local execution environment. For third-party models like Sol, this means the wait activations are loaded into an ephemeral memory space that is wiped the millisecond the final token is streamed back to the user. There is no persistent storage volume and no local logging permitted by the hardware scheduler. This architecture ensures that even if a model provider's account is compromised, the attacker finds a clean slate because the data only exists in a transient state. The signal under the noise. The transition to PCC 2.0 represents a pivot from policy-based privacy to proof-based privacy. By decoupling model utility from data ownership, Apple has created a template for how high-parameter models can be deployed on sensitive enterprise data without the liability of traditional data residency. We have moved past the era where we have to trust a company's terms of service. The new standard is to verify the physical state of the silicon before the compute begins. This shift forces the rest of the industry to either adopt these verifiable trusted execution environments or explain why they still require clear text access to user prompts for optimization. For builders and researchers, the implication is clear. The bottleneck is no longer how much data you can safely send to the cloud, but how quickly you can verify the remote hardware. Watch for the first independent audit of the PCC ledger this fall. If researchers find a way to bypass the hardware-enforced memory flush, the entire trust model for third-party AI will require a complete architectural rethink. Subscribe for more.